Ladies and gentlemen, today we're going to learn about work, power, and energy. Alright, so if we take a look at the kinds of energy, we have mechanical energy, sound energy, light energy, thermal energy, and chemical energy. But what you might have to ask yourself is, what does all this energy do? From there, we can come up with this question: what is energy? Well, basically, simple definition is it's the ability to do work. Now we're going to go over the definition of work in a little bit. Okay, the unit for energy is joules, or a capital J. Now, energy for you, you might come across it more frequently as the unit for calories. Okay, so a calorie is a unit for energy. 4.19 joules is 1 calorie. Okay, so the thing to keep in mind is that energy can be expressed more specifically by using the term work. So what is work? Now, you might think that you do work at school, and that's because the everyday definition, the vocabulary for work, is when you do something. However, the physics definition is not the same. Okay. Long story short, work is when you exert a force on an object, and the object has a displacement. The object might be like a can of soda, a cup, or even your own weight. You are an object. Now, if we take a look at the equation for work, you might see in multiple forms. The first form, we have work is equal to the force that is parallel to the displacement. All right. We can also write it as force times the displacement times the cosine of theta. And the cosine of theta will come in handy because of the very definition of work. And you'll see a couple examples in a bit. Sup, pros? Today we're going to work out. Here we have Andy, and he's going to do the bench press. Okay. Now, taking a look at his bench press in terms of working out, we can see that he can get a good pump in if he lowers her and raises the bar. However, that's the everyday worldview of work. Let's take a look at his exercise in terms of physics. Now, if we look at Andy's hands, his hands are pushing up, so he's exerting a force up. However, when he lowers the bar, that is in two completely different directions. Therefore, Andy is doing negative work. Okay. However, if his hands are pointing up and the object moves up, he's doing positive work. Now, remember the requirements for work. Your force and the direction that the object moves in has to be in the same direction. So, let's take a look at how much work he's actually doing by doing a couple of reps. Negative work, positive work, negative work, positive work. All this working out in terms of physics means that Andy's not doing any work at all. Any positive work that he's doing is being counteracted by the negative work that he's doing. Now, if we take a look at the viewpoint from the Earth is pulling down on the bar. However, when the bar is lowered, the Earth is doing positive work. But Andy is doing negative work. So when Andy raises the bar up, the Earth wants to pull the bar down, but it's going in the opposite direction. So the Earth at that moment is doing negative work, but Andy just did positive work. Alright, so Andy right now is going to get some big guns. He's going to do some bicep curls. Now, from the former part of the video, we learned that whenever he curls up, he's doing positive work. And when he curls down, he's doing negative work. So he's actually not working out. Now, we know that he's doing positive work because he's exerting a force up, and the weight moves up, and when he pulls it down, the force is up, but it moves down. So we have two things in the same axis. The force is up, and the direction is down. However, let's say that Andy is holding the weight up, like here. Okay, so his hand is exerting a force up, but Andy walks forward. And then he walks backwards. At that moment, did Andy do any work? Well, let's take a look. Andy has a force from his hand pointing up, but he walked forward. That means that because the two are in different directions, he is doing no work by just walking across the room. Alright, after all that strength training, Andy needs to do some cardio. So here we have Andy on the treadmill, and we can see if he's actually doing any work at all. So one of the requirements for work is that there has to be a displacement. if we take a look at Andy, he's not moving from the spot that he's standing in, so he has zero displacement. Now, it doesn't matter how much he walks or runs, because his displacement is zero, he did absolutely no work. So, here's a chart that showcases the different kinds of work that you can do. For example, in the first box, we have an object that is moving for example, in the first box, we have a force that is pulling at an angle, but the object is moving from side to side. That means it's only in the x direction that it's moving, so the y component of that force vector does no work. Okay. In the second example here, we have a force exerted in the same direction as the displacement, therefore it's doing positive work. In the third example, we have the force exerted in the opposite direction of the direction that it's moving, therefore it's doing negative work. Now, in that example, the force would be most likely the force of friction. Remember, friction is always against the motion. Okay? And last but not least, in the final example, we have a force that is exerted up, like the normal force, but the object is moving to the right. That means the normal force is doing no work. If we were to do a lab, for example, where we pull or push an object across a certain displacement, and we measure how much force is exerted, and we measure how much displacement the object travels, and I would ask you to make a graph. Now, graphs are very important when we're talking about work. What we would create is a force versus displacement graph, okay, where the y-axis will be the force and the x-axis will be the displacement. If I were to ask you to find the work from this graph, what you have to look at is the term called area under the curve. And basically, a curve can be a curve like a parabola shape or even a straight line. Okay, a straight line is considered to be a curve. So if we take a look at the area, in this case, in this example, is highlighted in green, we can find the area for that triangle by doing 1/2 times the base times the height. Now, if the area of the curve were to be, let's say, a square or a rectangle, it would just be base times height. So whatever number you get from finding the area is the amount of work that you did on a object. Now let's talk about power. We have 3 examples here of different athletes. We have a golfer, a quarterback, and a sumo wrestler. Who do you think is the most powerful? Well, some of you might say, well, the sumo wrestler is pretty powerful. I mean, look at those big guns, right? But in terms of physics, the golfer is actually the one that's doing the most work around the shortest amount of time. That's the definition of power. So simply put, power is how much work you can do in the shortest amount of time. Okay? So if you're not powerful at all, or if you have little power, you do a certain amount of work over a long period of time. Okay? The definition, or the unit for power is a watt, or 1 joule per second. Everyday people like you and me, we consider watts to be something for light bulbs, and it's a good visual representation of what power can be used for. Okay, another way to describe power, or another unit, is the horsepower, which we use to describe stuff like boats or cars or trucks. Okay, and the conversion is right there. So what is the difference between work and power, other than the very definition itself that in order to have power you must do work? Take a look at this example here. Okay, so we have a person and you are walking up a long distance of stairs, and you have to stop because you expended so much energy. On the other hand, you have a person who runs very quickly up the stairs, but that person might become really exhausted because 1, stairs are exhausting, but 2, you did so much work under a short amount of time. So in that case, you are limited by the power that you are able to exert, or how much energy you can convert in a short amount of time. Alright, so let's do a quick recap. Right? So when you go to work and you come back home, your total displacement is 0. So after a long days of work, technically you're not doing anything. And if any teacher gives you a lot of work to do, you're not doing a single thing, because all you're doing is sitting at your desk and moving your pencil around. You're not doing any work at all. So let's all stop complaining and let's do some work. No, that's a bad idea.
You used my joke. Yes.
How can we end it? So quit your complaining and get working.